This empty house. I don't like walking around it. You better listen to the words that I say. Good morning, good afternoon, good evening. We are back and better than ever. Still extremely excited about talking about the calculus. You like the calculus? I know you do. So we are going from the product rule to the quotient rule. And we use the quotient rule when things are being divided. Rational expressions, say you. Here they are. You probably think of them as fractions, and fractions can be thought of as division problems. So if we have functions of this form, we can use the quotient rule. Okay, well, what is the quotient rule? Well, I'm not going to go through this step by step. I'm just going to give you the overview of it. And if we have some function q of x, that is two functions one being divided by the other, u over v, then if we solve for u, just look at this first step, we get u of x equals q of x multiplied by v of x. Well, to take the derivative of u of x, we would use the product rule. And then all this is just solving for the derivative of q, and it ends up like this big giant mess. That is the quotient rule, but it's really not. It looks complicated, but there's an easy way to, well, not easy, but an easier way to remember it. Okay? So here it is. If q of x equals u of x over v of x, then its derivative is equal to, again, I don't like the way that they have written this. I will show you how I like to think of it. I would rather have them say v du minus u dv. And if you remember from the product rule, that's how I wanted you to do the product rule. Product rule is v du plus u dv. Okay? The difference is then we take the function v and we square it. Okay? And so they kind of do it here, but I would say v du. It just kind of flows better. V du minus u dv all over the function v squared. And this is how it looks like on your formula sheet. So we do have the v du minus u dv all over v squared. And that's what we will be using to use the quotient rule to find the derivative of rational expressions. Okay, so use the quotient rule to find dy dx if y equals blah blah. Okay, well, the first thing you need to do is identify your function that is u, that's in the numerator, and your function that is v. So sometimes it helps, especially when you're first starting out, to just go ahead and write it out. U equals 1 plus 3x, and then take the derivative right away because we're going to need it. U prime is equal to 3, or the derivative of u. And v is equal to x squared plus 1. And so the derivative of v is equal to 2x. And now we just have to use our formula. So for our function y, dy dx equals v du. V multiplied by the derivative of u. So that's x squared plus 1 multiplied by 3. So I'll just put that 3 out in front because it looks better that way. Minus u dv. Well, u is 1 plus 3x multiplied by the derivative of v. That's 2x. So I'll put a 2x in front of there. And that is all over v squared. Well, what's v? X squared plus 1 squared. Okay? And you might be looking at that and say, that is a huge mess. It is a huge mess. But you don't, most of the time you don't need to simplify it, because if I said, okay, what's the gradient of the tangent to this curve at x equal to, I don't know, 2? So you would be finding y prime of 2, right? And then you would just be replacing x with this 2. So why bother simplifying it when everything is going to turn into numbers, which are much easier to deal with than a whole bunch of algebra. So, don't simplify unless you're asked to or you absolutely have to. But here you go. That's a perfectly good answer for the derivative using the quotient rule. And I only have one more example. How about them apples, huh? Find dy dx if y equals square root of x over 1 minus 2x, the quantity squared. Well, I am going to immediately rewrite that square root of x as x to the 1/2 power. And I will leave 1 minus 2x as squared. Okay? And then I will identify my u and my v. So u equals x to the 1/2 power. And then du, or u prime I like to write, is equal to 1/2 x to the negative 1/2. And v equals 1 minus 2x, the quantity squared. And the derivative chain rule is going to be 2 times 1 minus 2x, the derivative of the outside, multiplied by the derivative of the inside. So the derivative of the inside is negative 2. I am going to simplify that. That's just too easy not to simplify. At least the 2 times the negative 2, negative 4 times 1 minus 2x. And what the hey, let's just go ahead and distribute that 4. You don't have to, but I'm going to because I just feel like it. Negative 4 plus 8x, which I'm going to write as, oh my gosh, I'm going crazy, 8x minus 4. Okay. All right. So, dy dx is equal to v du. So v is 1 minus 2x squared. We got a whole fraction thing going here. So this is 1 minus 2x squared. There's my v. Multiplied by the derivative of u. I'll put that guy out in front. 1/2 x to the negative 1/2 minus u dv. Well, what's u? Well, it's x to the 1/2 multiplied by the derivative of v, which I took all the way to 8x minus 4. I didn't necessarily have to do it, but the simplification was so easy, I just felt like I had to. And all over v squared. So v is 1 minus 2x squared. Squared. Yes? Squared. Okay? And you should probably simplify this, at least the exponent. Exponent to another exponent, we multiply them, so 2 times 2 is 4, so I can write this guy as 1 minus 2x to the 4th power. And we are done, really. The only other thing I might do if I had to find the gradient at a particular value of x is I might rewrite this, just to be safe, as 1 over 2 root x times 1 minus 2x squared. I mean, you could even put that in the numerator. Minus square root x, rewriting x to the 1/2 is square root of x, times 8x minus 4, all over 1 minus 2x to the 4th. Okay, but you only simplify what you're sure of, or when you're asked to, or when you have to evaluate at a particular value of x. And this form probably is not conducive to you being able to evaluate at, say, x equals 9 or something like that. All right, that is it, and I am out.